All right, this is a totally unique talk just for you guys. I haven't really practiced it in the last 2 days, but I am Brad. I worked on the Go Standard library. You can find me on the internets under Brad Fitzy sort of things at Twitter, Golang. I spent a lot of my time working on my side project Camly Store, but this talk is about HTTP and HTTP2. My previous life I did open sourcey internet things, and I still work on open sourcey internet things. So first I'm going to go over HTTP and kind of like the history, where it came from and where it is going now, and then I'll jump into writing lots of code, or showing you lots of code at least. So I got to start with Gopher because, you know, Go talk. The Gopher protocol in about like 91 or something kind of looked like this. The part in red is the part that your browser, or whatever you called a Gopher browser, would send. The client would send to the server. And so in this case, I wanted to get like, you know, the /reference path from a server. And the response from the server was a bunch of lines that were like space or tab separated. The first byte on each line was like the content type, where like, you know, 0 was directory and 1 was text file and 2 was GIF and like 7 was a movie. You know. So anyway, it wasn't very extensible, but there was some metadata. About the same time, HTTP 0.9 was coming about. You can see that they added a verb. So we have get, but I guess there's no content types. Everything has to be HTML, I guess, at this point, or the browser has to know. And after you're done with the request, both sides just kill the TCP connection. Later on, we have HTTP 1.0 that actually adds a version at the end, so it starts to be extensible. There's key value in both the request, like user agent and cookie or whatever, and the response. So now you can say things like content type. And at the end, it just disconnects, just like before. HTTP 1.0 evolves a bit, and browsers add connection keep alive. So if the client says, yo, I'm smart, I know what I'm doing, I'm not going to hang up on you at the end, so maybe you won't hang up on me either. And the server acknowledges that and says, yeah, okay, connection keep alive, and then you can keep reusing that TCP connection. So 99, HTTP 1.1 comes out, and now that keep alive thing is the default. So unless you explicitly opt out of it and say connection close, it's implicit that you're going to keep the connection open. Host headers are now required, so for virtual servers, there's a shortage of IP addresses. IPv4 is going to run out imminently. It maybe still is. So yeah, it's about the same. So now we have HTTP 2. It looks a little bit different. As you can tell, HTTP 2 is a binary protocol, and it's no longer text. And instead of one thing that you're requesting at a time, you can request tons of stuff at a time and get it back in any order. And it's still pretty clean and consistent, unlike all the kind of hacks that have accumulated in HTTP 1 over the time, and to deal with buggy clients and buggy servers and undefined things in the spec. But other than that, it doesn't really change the fundamental nature of the web. It doesn't change how developers write code, people on servers write code. It still has all the same verbs, all the same semantics about cookies. There's some people on the internet who really hate HTTP 2 because it doesn't fundamentally change everything. They're like, you know, we should change the whole session model and cookies are evil, blah, blah, blah. But HTTP 2 is just supposed to be a better wire format for HTTP, so it's not that interesting. One thing that's kind of notable that is in practice, HTTP 2 is only over encrypted channels, over HTTPS, and that's largely pragmatic. I think I have a slide about that. But so you can notice from the times, the dates here, you know, this is like 91, 91, 96, and then like nothing. You know, nothing really happened in this whole time. They tried to add pipelining to HTTP 1. It's in the spec. There's a bunch of stuff that's in the spec that no one actually implements. And if you actually try to do pipelining on the internet, that's when your browser sends a whole bunch of requests all at once, and you expect the server to reply in the same order. In practice, no one enables that because some servers can get confused by it and just don't reply with anything. And sometimes you have a transparent little helpful proxy in the middle. Maybe it's you know, something at your company or some guest hotel Wi-Fi that's trying to be helpful, or maybe something injecting ads or malware into your page, and it gets confused by pipelining and it craps all over the responses and the internet breaks. So in practice, no one does anything kind of crazy because the internet is so broken in the middle that unless it's encrypted end to end and you actually trust the other side, you can't really negotiate up to things. So the only real innovation we got in HTTP was browsers just started opening up more connections at a time to servers, thinking, well, I guess servers are more beefy nowadays, so instead of 1, we'll do 2, and nowadays, like Chrome will open 6 connections at a time to a server. The end result is kind of like what you saw in that demo. Make this not full screen. Where, yeah, like on this little Gopher tiles demo here, if you have like typical 200 millisecond latency, that's Chrome with 6 connections at a time, each one taking 200 milliseconds. So you can't have much stuff in flight at a time. Whereas like a normal 200 millisecond sort of latency to something on like another continent, it still takes 200 milliseconds for every tile to load, but your browser just sends over 1 TCP connection instead of 6, says, yo, give me these 180 tiles. And then the server's like, sends them all. So HTTP was kind of boring for a while. 2009-ish, I think, plus or minus a year or so. Google at this point had a browser and has lots of servers. And so Google kind of like, well, we can experiment with different things. So Google started advertising that the server during like the TLS handshake, hey, I support this version of some other protocol that's HTTP-ish but not HTTP, and Chrome would see that and say, okay, I'll speak this. And it's basically HTTP2. There's some things that are a little changed with compression of headers and some details about framing, but Facebook and other people got really excited about this and endorsed it, and the ITF became like they started doing stuff again, and they decided to start doing HTTP2, and they took Speedy as the basis, and they've been refining that for the last I don't know, a couple years or something. So back to an HTTP request. This is that same request that I showed like here or here, or one of these. So all that get/example.com. So you can think of it like this, and breaking that down further, you can think of it like this. So there's 9-byte header. For every frame, there's a 9-byte header that says, okay, there's 12 bytes here, and these are the 12 bytes. And it is frame type 1, so there's 1 byte that says, I am a frame header in this case, so this is a new HTTP request. And the bits on here say end stream. That means this is a request that doesn't have a body. So it's like a get or a head as opposed to like a post or something that has a body. And end headers means the HTTP request key value pairs fit entirely inside this, as opposed to overflowing the max length of a frame that either could fit in a frame or that either side has negotiated as their max frame size. So sometimes you have to take the header and cut it up into multiple frames, and the final one says, I'm the end of the headers. And finally, you have the stream ID. So this is basically every HTTP request gets a unique number. They always start at 1 and they count up by 2. They're always even from the client and odd from the server, because HTTP2 lets you actually, the server, push responses that you never asked for. So the browser could say, I want /, and the server is like, oh, yeah, okay, I'll send you /, and I'm also going to send you favicon.ico and my JavaScript and CSS. And so it sends you a hypothetical request and that response to the hypothetical request, and then your browser's like, oh, now that I have it 200 milliseconds later, I do want that, and I already have the answer. So because these IDs are allocated on both sides, the client always sends even ones, or odd ones. So, and then this last part is the crazy HPAC encoded request, which is a new HTTP2 specific compression format that just puts all the key value pairs in there. It's there's a whole bunch of crap in there. It has some table. It's stateful over the life of the connection. So if your first request sends a really long cookie or a really long user agent, that's only transmitted once, and then subsequent requests refer back to it. And so you can say, oh, that was that 17th thing I sent once. And then that gets encoded, varant encoded to a couple bits, and like new unique things are Huffman encoded. So it gets really small. So I said there were that 1 byte that says for every frame what the frame type is. There's like 10 of them. These ones you can kind of ignore. This is that hypothetical, I'm going to push you a thing you haven't asked for yet. This is for letting clients reprioritize things that they've sent to say, oh, no, I actually want that JavaScript before the CSS or whatever. The main ones, though, are data. This is like the request body and the response body. This is making a new HTTP request. The continuation has to come immediately on the wire following the headers if it doesn't fit in one. Settings is not specific to an HTTP request. That's just the two sides agreeing on what their limits are. Reset stream is a way for your browser to cancel an HTTP request, either one that it was sending or one that it was getting the response for. You cancel your download or something. without killing the TCP connection. So you can cancel one download while still letting the rest of your page load, or something that's in another tab or another window keep loading. Ping is just a way for the two peers to see, hey, are you still there? Go away is for when the server wants to shut down. If you set like your Apache or whatever, you set your max keep alive to 30 seconds. Your Apache sits there, and after 30 seconds, after inactivity from the client, the server's just like, okay, I'm closing it. But it could just be that the browser, after 29 3/4 seconds on the other side, says, all right, time for new request. And one's going across the ocean this way, and one is shutting down this way. And you don't really know if the server got it before. You never got the response because it was sending you a TCP reset, and you were posting your credit card details in this direction. And was your credit card charged? I don't know. So this is a way for HTTP 2 servers to properly shut down with two sides kind of agreeing about whether something went through. The way HTTP is upgraded to HTTP 2, if it's HTTPS, it's easy. There's an extension to TLS that says, in addition to agreeing on what cipher suite we're going to use to encrypt all this stuff, and SNI is the server name indicator that says what host name you want to connect to before you start encrypting stuff. There's something it was called Next Protocol Negotiation, and now the same basic thing is called ALPN, and it's a way of saying, after we're done doing this little TLS handshake, what are we going to speak after this? The default is, depends on the protocol port number. For browsers, it'll be HTTP. But if both sides advertise that they speak HTTP 2 or some version of HTTP 2, currently it's draft 14, then you just go into that mode afterwards. For HTTP, there's a way in the spec, but the way in the spec is basically there for politics, and nobody is really going to implement it. But so it's not even worth mentioning. You can kind of ignore that it exists. So let's write a Go implementation. All right, let's see if that's big enough. Get adjusted as we go. So the first thing we're gonna have to do before we do all this crazy stuff is we're gonna have to actually read some of these frames. That red thing I showed with that 9-byte header and the 12-byte body or whatever. So I don't know. The naive thing to do is say, okay, we're gonna write some function called read frame, and it's gotta return something. Maybe it'll return a frame, but we don't really know exactly what a frame type is yet, and probably it'll return an error. Remember, the frame looks like this. There's the 9-byte header, there's 3 bytes of length, a type of flags, a stream identifier, which is 31 bits, and one reserved bit that is not currently used. If it's 0 or 1, it doesn't matter, we have to ignore it. And then this stuff. So probably a good place to start is just reading these first 9 bytes. So we make a little type called frame header, and it has a type, which is the frame type, which is just a named type for a single byte. Flags, which is a named type for just the 8 bits of flags. The length, there is no uint24 type in Go, so we'll use uint32, and then the stream ID. Frame type, we give it a name just so we can have constants that are of the right type, and also so we can have things like, we can give it a good string method on it. So when we're writing debug stuff, when you're working with binary protocols in particular and you get some crap in and it's not what you expect and you go to log it, you don't really want to see binary crap logged to your logs. You would like to see some stringification that's beautiful of the stuff. So we make a little string method there that if it has a known name, we print out its spec defined name. If it's some weird frame type we don't know, we stringify it as unknown frame type 17. Likewise, there's a little flags type, and just for cutesiness and for readability, I have a little has method on it. So rather than having all this bit math sprinkled throughout the code, I could just say, does it have that flag? Does it have that flag? And then define a bunch of Go constants with all the flags that are defined in the spec. Notice also that here, even though they go 0 to 9, I don't use iota there. Only use iota when you're actually defining your own things where the numbers don't really matter. You just want some internal identifier. But if you're ever interfacing with the outside world and the numbers have a meaning, actually spell it out. It would suck if I used iota here and then I rearranged thing, and now all of a sudden I'm thinking of frame settings as a frame window update or whatever. So then, again, I have a map of all the names of the flags, and then I could write I could write a better little string method for my frame header, and then I can get output like in my logs. I could see, oh, that's a frame header, that's a headers with the end stream and end headers bit set, and also this undefined unknown bit 2 is set. Maybe, you know, there's a new version of HTTP2 that defined that, and I don't handle it yet. Stream ID 1 and the packet or the rest of the frame, the data part, is 17 bytes. So always write little good string methods, you know, for debugging. Anyway, so we're back here. So we have an IO reader that we're going to be reading frames from. First, we're going to do read frame header. So we know the frame header length is 9, so we have this constant in the code. You could write it like this. You could say a little local variable called buff, which is a 9-byte buffer, local variable. And you call read full into it. And so read full returns an error if it doesn't get exactly how many bytes you asked for. So bail out. Otherwise, we know we have 9 bytes, and you could unpack the length and the type and stuff. Mask out that reserved bit that we don't care about. But the problem here is that this buffer, escape analysis would normally keep this on the stack, but because you're calling through an interface value, escape analysis doesn't know what the reader is going to do with that buffer. So conservatively, it just has to heap allocate this. So this will always generate 9 bytes of garbage. And that's fine, goes garbage collected, this will work. But throughout the design of this package, I've tried to keep garbage to a minimum, so this could be like pretty high performance. So instead, I decided to have the caller pass in the little buffer for me to read into. So the caller has to supply 9 bytes of memory, and then I read into that 9 bytes of memory. So write some little tests for it. Always write tests. Here's a little table-driven test where I have some input, have 2 cases for ignoring the high bit or not. Here's the high bit is off. Here the high bit's on. Make sure they have the same stream ID, and write out some good error messages. So there's actually twice as much test code as there is in this whole package as there is real code, and it's found tons of bugs, so it was useful. Okay, so now we're back to read frame. We have a working frame header, and we have to supply this buff, but we don't have a buff. So it's time to turn this from a function and into a method. So we actually make a framer type, and we will actually put those 9 bytes just on the framer struct, and we'll just reuse this framer forever for the life of a connection. Every time a new connection comes in, we'll make a framer and just use it. There's my reader. We'll also be using this to write, so there'll be a writer and so much of other stuff. Here's a little constructor, get a framer, and set up read and write. Probably add some stuff to that later. So now we have this method on framer where we read the frame. We have the buffer now, so we can just read into those 9 bytes. And okay, now we have a frame header. So what is a frame? It could be a struct or an interface. I've decided to make an interface. This may change, but currently it's an interface as anything that has a header method, and it returns the frame header. And it's up to the caller to do a type assertion to see, is it a headers frame, is it a settings frame, is it a window update, or it can look at the header and look at the type from there if it prefers to do that. And it also has this invalidate method. So the design of this thing is all these types, like headers frame, settings frame, windows update, they have a bunch of accessor methods to get at the body of the payload, which could be like, a megabyte of data or something. Some post request is flying through your server and you're just a proxy or something, and you want to read it and write it. But you don't want the caller to potentially have or be able to own that memory for long term, because then it would just be like megabytes of garbage flowing through your server and that you're just generating all this garbage. So instead, the semantics of our framer is that whenever you read a frame, you can access it, you own it until you read another frame. So the framer is going to call this invalidate method whenever it reads a new frame. And then the caller, anyone who violates the rules and accesses the stuff in the future will blow up, and we'll say, you violated the documentation. So in addition to on our frame header, I also added this valid byte. And this is just where we keep track of internally of, have you broken the rules or not? Can you actually access this? And then in the frame header, I have the invalidate method where I say, okay, it's no longer valid, valid false, and then I have this check valid saying if it's not valid, I blow up, and your program has an internal error. And in practice, no one really can access these, or no one needs to use these, so it's fine to kind of be strict. So then here's an example of one of the 10 frame types. Here's the headers frame. I just embed the frame header, so it automatically implements the frame type because frame header implements invalidate, so I don't actually have to do that. And now I have accessor things like header block fragment, which gets those 12 bytes you saw on the first slide with that HPAC encoded headers. And first I say, okay, let's make sure the caller owns it, and if it does, then we return those these bytes that are right here. And then I have a little comment saying these aren't owned. And then I have a little couple convenience methods like headers ended that just is an alias for this, so the caller doesn't have to type all that crap out. And remember that this is just a bit check. So now we're starting to look like this. We have a max read size. This is one of the things that two peers negotiate. We have a little buffer. We keep track of the last frame that we read because we have to invalidate it. There's a little a function here where the caller, that when it sets up a framer, can define what the memory allocator is. It could just allocate new memory for every frame. You read a 1 meg frame in. You're like, okay, I need to allocate a make byte slice of 1 meg, but then that could be garbage. So instead, it's kind of pluggable, so you can define how that works. The default is that it just keeps a byte slice and it makes it bigger if it's not big enough, and it just keeps reusing this byte slice. So in practice, every framer will eventually grow to the max frame size and have one big buffer sitting around. But if your framer size is like 16 meg or something, which is the max, or 24 meg, then every idle connection would just be holding on to 24 meg while your browser is sitting there doing nothing. And with HTTP2, the idea is that there'll be browsers with tons and tons of connections, or you'll have tons of clients, and all those browsers will have one idle connection to your server. So you might be sitting there with hundreds of thousands or millions of idle connections, and you don't want each one of them just sitting onto 16 meg of memory for no reason. So the getReadBuff function, the idea is that it would pull it from a pool when your connection's actually active and throw it away and give it to somebody else the rest of the time. So now we have that read frame header part. Now I made a little type called frame parser, and it's just a cutesy name for a func that takes a frame header and takes the rest of the frame header, and I document that any frame parser, the length of this payload is guaranteed to be this length that was declared in the frame header, so the caller of this will verify that or guarantee that invariant, and then it returns a frame and an error. And then I define all the frame types and their parser functions. And then I have a little accessor that, given the frame type, the 1 byte that says what it is, I either look in the map, and I guess I should make this not be a map and make it just an array for small things instead. But during development, it was useful to only have 3 or 4 types in here in a sparse map. But so I look up the function, and if I don't have a function for that frame type, maybe there's some HTTP2 extension that's in the wild that I don't support, and the spec says you have to ignore it, I just return the parse unknown frame type, where I just skip over it and do nothing. So now our read function looks like this. If we've already read a frame in the past, we invalidate the previous one. Then we read the 9-byte frame header. We see if the 9-byte frame header declares that this packet is over the size that the 2 peers have already negotiated. And it starts out, the spec says it starts out at 16K. And if one of the peers upgrades it, then, and they agree, then it goes up. Then we get a buffer to actually read the rest of it into. Maybe this is 12 bytes, maybe it's a meg. And then we read into it, and read full returns an error if it's not the correct size exactly. And then we look up our type frame parser, which could be the unknown frame type, and then we pass it the header and the payload. And then that returns a valid frame. So here's an example of one of the simpler ones. Here's a data frame. The data frame parser says, is there a stream ID associated with this? If not, if it's 0, that's kind of a bug because the spec says data frames must be associated with a stream. So if it's 0, you have to reply with a connection error. So we reply with a connection error. Otherwise, we make a data frame with the embedded frame header. We see if it's padded. The spec lets you pad your data and kind of like hide the size of your communications in case that was revealing something to people. So you could put in like random junk data. So if it's padded, skip over that stuff. Ignore the padded size. And if the padding size doesn't match reality, then blow up with a connection error. Otherwise, return the frame. There's some stuff in the errors file about an error code is the UN32 and all the values from the spec. There's errors can either be a connection error, which closes the whole connection hard if they violated the spec so hard you really can't continue. But if it's an error specific to a stream, which is to say an individual HTTP request, you can have a stream error that just like kind of kills that one request. For writing HTTP frames, there's a whole bunch of little convenience functions like this. Write a data frame, write a settings frame, write an acknowledgement of a settings frame, ping, go away, blah, blah, blah. They kind of look like this. Wrong tab. we start off calling an internal start write function where we say the frame type, the flags, and the stream ID. And then we put some other like packed binary values in there. Here we go over all the settings you pass in, and we write the uint16 of the setting ID, the uint32 of the value, and then we call end write. These functions are kind of fun. Start write, oh, and here's a write settings ACK. That's a really simple one. We start write, set the ACK bit, still stream ID 0, and then we call end write. Oh, and we let you do illegal stuff too. So by default, we don't let you write illegal frames, but if you want to mess with other servers on the internet and see how they break, which is fun to do, you can set the illegal writes. So the start write function, we take this buffer, which is our write buff, just like we had the 9 bytes to reuse for sending or to read frames in. We also have a buffer that we use to prepare to send frames out. So first we append onto it and we reserve 3 bytes. We don't know how big this thing's going to be yet, but we know we have 3 bytes that we're going to have to put the length in. So we put the 3 bytes there. We put in the frame type, the flags bit, and the stream ID. And then you push all that other stuff. So this is appending to wbuff. And then the caller is like going to push data or uint32s or uint16s or single bytes. And now at the end, we calculate how big is this thing? How big is this frame we're about to send? So it's the length of the buffer minus the 9 bytes at the beginning. And if it's bigger than the size of a frame that we can't even encode it in 3 bytes, then we just blow up and we say we can't even encode this thing. Otherwise, we fill in that length again. I kind of abuse append here. It avoids some bounds checks. It doesn't really matter. It's more cute than anything. That I put this length in those 3 bytes we reserved that were previously 0, and then we write it out to our writer, which could be the network. It could be a buffered IO writer, and then return error. So yeah, then there's little cutesy helper functions like this: write byte, write bytes, write uint32. So write data kind of ends up looking like start write, append some data, end write, setting up the flags as necessary. So writing a server, the way you upgrade to HTTP2 is, like I said, it's over that new NPN or ALPN thing. In Go, all you do is when you make your TLS listener, you say next protos, and you just list the protocol strings you support. For HTTP2, the official one will be called H2, the string H2. But during this internet-wide testing phase, every draft specification gets its own protocol thing. So you can test a server supporting 11 versus 14 versus 16. And currently, most people on the internet are supporting H2.14, or people who are playing the game are using 14. All of Google servers are currently advertising H2.14. So then you accept the connection, you do the little handshake, decide your cipher suite, verify the host name. And then if you call the connection state accessor on the TLS.con, you get this little struct out. And one of the fields is negotiated protocol, and negotiated protocol is mutual. So if that is true and that is the string you wanted, now you're speaking HTTP or whatever, speaking whatever protocol. And since about a year or so ago, maybe Go 1.1 or 1.2, there's this little map in your server where you can have a map from a protocol name to a function to take over that incoming connection. So you can hijack incoming HTTP connections to Go server and have something else handle it. So this is in the standard library. Probably nobody's been using it, but I was prepared. And so HTTP2 has a little function called configure server that hooks into that and populates this map if you don't already have it. It won't override it if you do. And defines a function that takes your old HTTP server and your new configuration and the HTTP handler you meant to be called, probably like the HTTP default servmux, and then calls the internal HTTP2 handle confunc. And handle confunc gets all this, so we have your server, which is has your HTTP2 configuration, how many max concurrent connections you want, and all that. But I wanted to show one fun slide about kind of the design of the Go routines. So oh wow, there's absolutely no color on this. So for every incoming connection, we're going to set up logically three to four Go routines. There's one main Go routine that I call serve, which has all the logic. It has all the channels that's sitting there in a read, select, or forever select loop talking to all the other parts, and it never blocks. It owns all the state. It has all the policy about flow control and settings and what the sides have negotiated. It keeps track of like which HTTP handlers are running. And then we have another Go routine called the read loop. It's just sitting there and it's just reading from the socket. It's basically always waiting for 9 bytes. Like, give me another frame, or once it gets to 9 bytes, then reads the rest of it. Once it has a full, complete frame parsed in memory, then it sends it to the serve one that decides what to do. Likewise, there's a Go routine that's always writing to the network, sending whatever frame, because this could block too. And you don't want to block all the other stuff going on in your server. This one actually was a Go routine that was sitting there reading from a channel to say what to write, and then writing it, and then saying, okay, I wrote it. But just the communication between the Go routines to the writer to go back and all this stuff, that ended up being more costly than just creating a Go routine every time we had a frame to write. So if we're not writing a frame, I start a Go routine, write a frame, and tell the serve loop, tell this guy, yo, I'm done. And then it keeps track, okay, there's not a frame being written now, and the next time it needs to write a frame, it starts another one. And this is important because Go routines used to be 4K, and then they were 8K, and now they're down to back to 2K, and maybe they could get shorter. But so that would be 6K of memory for every idle connection, and if you want to have hundreds of thousands of these, that would be a lot of wasted memory. So I'm actually going to try to get rid of this one too, and make this one only active when there's something to be done. So for every idle connection, you'll just have one Go routine sitting there blocked on read, and then as necessary, if it's actually doing an HTTP handler, it'll wake up other ones as necessary. And then every HTTP handler, as normal, like in the Go HTTP or the net HTTP package, will bring up its own Go routine. And those will talk to this one, and all the pushback to for flow control reasons will happen kind of here, and not let these guys write anymore. So I showed this kind of pretty slide, and the reality is it's not pretty. It starts up, it makes a server con type, and it initializes a lot of its state, its maps of policies. It's every connection has an HPAC encoder and HPAC decoder that are both stateful. The framer for reading and writing frames. And so it sets up all this crap and all these data structures, and then calls serve. And serve is that main Go routine that never blocks. So serve at the beginning has a whole bunch of defers to kind of shut down the other Go routines, clean things up, close channels. And then the first thing it does is write a frame to the other side and says what our policy is, what are our settings, max frame size, and whatnot. And then the rest of serve is just this big loop, this big for loop that just waits on channels to figure out what's happening. Frames are coming, frames are going, handlers are coming, handlers are sending stuff, and timers and whatnot. I mean, that's the whole loop. There's not many things that can happen. You wrote a frame, someone wants to write a frame was received, somebody read from a body, so your HTTP handler called request.body.read and slurp some of the data. And as you do that, you send new flow control tokens back to the other side. Say, okay, you can send more now. The read frames Go routine is pretty simple. Like I said, we can only be reading one frame at a time before it's handled, and then we can read the next one. So we make this little gate, which is just I'll show you here. A gate is just a channel of empty structs, and then it's just named, so you can have cutesy methods on it called done, and then call sites could look like gate.done rather than gate send of struct. I called it curly the other day or something. Or you can have wait, and which just receives from it. So now we have we make a gate that we use once for the lifetime of the connection. We read a frame, we send it to the serve Go routine, who will process it, and whenever and we send the frame and the gate, and which is just a little type frame and gate, which is small, it's, value type, doesn't generate garbage, and once the other side is done processing it, they call done, which wakes up this wait, and then it proceeds and reads another frame. I think I showed on this slide, I didn't really talk about it, all the code and this stuff. So we have these 4 Go routines potentially going at a time. The read Go routine, the write Go routine, the serve one, and the HTTP handler, of which there could be a bunch, but they're all kind of classic. They're all the same. It could be confusing to know which code is running on which Go routine, and you could write English documentation saying this data is guarded by this mutex, or this data can only be accessed by this Go routine. But it's easy to accidentally violate this. So I made this little helper type called a goroutine lock. And a goroutine lock basically just keeps track of which goroutine it was created on. And then you can say check. And basically this blows up. If this ever enters on a different goroutine, then it says you're doing it wrong. And the whole program crashes. So this is just to keep me sane. So there's a little goroutine lock, which is just a uint64. And when you create it, it just looks at the current goroutine ID, which is you're never supposed to have access to, but there's hacky ways to do it. And unless you have a really good reason, I would say never do this. But I have this all disabled in real programs. So normally when you do this, it does nothing, and it just returns. But otherwise, yeah, it creates this goroutine lock, and you can say check that I am on this goroutine or check that I am not on this goroutine. So then in all the code, there's different methods like write frame from handler that tells the thing, check that I'm not on the serve loop because it would deadlock if you were, and otherwise this blows. And then there's this one like write frame. This one can only be called from the serve goroutine. So there's English as well to tell you the rules, and then there's this guy to make sure you follow the rules. So all the code kind of has that if you're looking at it and you're confused. Somebody proposed that we add that to the standard library. I don't know if that will go in. I expect some people to argue, but at least by telling all of you, maybe people tell me that would be useful. I would have arguments to argue for it. There's a whole frame schedule. So everything HTTP2, which I can't say, has a priority. So the browser can say, I want this JavaScript, CSS, and HTML, but I want them in kind of this order. Or first I want all the text and the HTML and CSS, and then I want the images. So the browser can choose like how many flow control tokens to give to the server, and the server kind of has to it doesn't have to, but the priority can be ignored, but a good server should respect the priority. So there's a whole frame scheduler. There's all these things we may potentially need to send to the browser, but the connection is only so slow, they're on a phone or whatever, and so we have to decide what to send next. So the frame scheduler says, are we currently writing a frame? If we are, okay, we can't do anything. Otherwise, if we need to send certain things that acknowledge their settings or tell them to go away because our server is shutting down, we send those things. Otherwise, if we're not in shutdown mode, we ask the write scheduler what is the most highest priority thing to take, and that looks at various things like, I don't know, priorities of things, and it returns one and tells you whether it returned one, and if it did, you start and you send that frame. That is about all the code I have there. I also wanted to say that there are tons of tests. I think I told you there's twice as much tests as there are code. And so one thing I found useful, oh, the colors are ugly. Font lock mode. I find it helpful to make little kind of server test helper functions to make your test code less repetitive. So I had this little type here that I called server tester. It just has a bunch of stuff like a framer and HTTP server and some buffers and HPAC encoders and all this stuff. And then I could hang all these methods off that, and I can make this little server tester that holds my testing.t or my testing.b in it, and various functions. So then I could actually write all these things that are tests. I'll make it a little bigger. Test at the server when it gets a post with no content flick, the end stream does that, versus immediate EOF versus post body that got 2 data chunks in it, with the second one closed. And for every one of those, I have little helper functions that that get run at a certain phase of the lifetime and check things check that the HTTP request was that, or this one, cookie, you got a packet, a frame that looked like that, and the cookie header that you got in your HTTP.handler was as expected. So if you actually run these tests, there are a ton of them. And so I can also run this against other people's servers by running it kind of as a child process and writing a little back end to it and seeing if other people violate the spec. And yeah, anyway, fun stuff. Andrew and I we wrote the HTTP2 client the other day on video, and so that'll be up at some point. We cut some corners, but we kind of got something working in 90 minutes, reusing all this framer stuff and all that. So that was kind of fun, and that's in the tree. So the most recent commits is me and Andrew hacking. yeah, the start of a video recorded HTTP2 client implementation. So the video will be there. This is a dummy link for now, but there's a little short link. But I will take questions so we can go have drinks and have a break or tea, afternoon tea. Yeah, Daniel. Yeah, the question is, are there any plans to do the server-initiated requests? I believe I have a pull request for this, and I see the author nodding his head. Yeah, I'll review it sometime. It's kind of a low priority, and it's kind of crazy. What's that? I'm sorry. Please repeat the question. Oh. Oh, okay, yeah, this is cute. So the spec is so gigantic that we thought it would be fun to actually check in the spec, which is this XML thing, and then we have, where's it called? So we parse this XML, and then we have something called spec tests, where we parse out every sentence of it, and then we can actually annotate in the tests. We could say we could say that this test covers that sentence of the spec. And so as new versions of HTTP2 come out and they update the spec and they add a new sentence, we lose test coverage against the spec, and we have to and if they change the wording, we'll have to update the wording here. But yeah. So it covers section 3.5, that sentence, and we'll see. We're not done annotating it all yet, but it'll be fun to see if it works. Probably not. The question is this the first spec coverage test in existence? I have no clue. But if it is, we're awesome.
Did you say something about using Docker for testing stuff?
Oh, yeah. The question is, did I say something about using Docker for testing? I did not. You might be remembering a previous iteration of this talk. Yeah, this is the first time. There are some tests in here where it's easy to test my own stuff and say, yeah, my own stuff does exactly what I expected it to do. It's another thing to see that my stuff actually works against other things in the wild. So we have a Docker file in the tree that gets a little Ubuntu trusty image and installs some crap, and it gets a new version of the ng HTTP2 C library that implements HTTP2, and builds curl and libcurl with that crap patched in. So this builds kind of an experimental version of curl that uses the HTTP2 that a lot of the internet is going to be using. And then once we have that Docker container, we kind of run it as a child process or whatever, and its own container hitting our server. So we basically do an integration test against another implementation hitting ours, and then we could verify that that curl saw certain things, that curl saw. We run curl-v, and we parse out certain messages from curl's headers and debug logs, and then we also make sure that we saw the right thing that curl should have sent to us. So kind of it's a sanity check. But then I added more stuff to the spec to verify that we do the right TLS. The spec, if you go to HTTP2 GitHub IO, go to editor's copy of the spec, TLS, usage of TLS things. It says TLS cipher suites, endpoints may not use or should not use the things that are in Appendix A, and there's a list of all the TLS cipher suites that are considered unsafe that TLS forbids you using. So of course I put that in the code. And then curl stopped working because they don't implement that yet. So filed a bug against curl, and I had to pull that into a little helper thing with a bool saying permit prohibited cipher suites. And now I had to add that option to the HTTP2 Go server, so you can set this on if you want to accept curl clients or not. But they're going to fix it. But there's a whole lots of stuff. Like when Andrew and I did the client yesterday, it worked against our own server, but it doesn't work against Google.com. So I don't know. Either we have a bug or Google has a bug, and so I was trying to debug it yesterday and I couldn't, or I failed, but I didn't have time. So there's all sorts of like interop issues still. It's getting pretty good, but this is why this spec isn't quite done, or this is why you don't see it more on the wild. But it's already, I think there was a presentation 2 days ago about HTTP2 that said it's already used something like 9 times more than HTTP2 is used 9 times more than HTTP 1.0, and it's 5% of the internet traffic is already HTTP2, and it's not even done yet. And which is also is 5% of the traffic on the internet is IPv6, which has been going on for 20 years, and this has not been going on for 20 years. So this is doing pretty good. Anything else? Tea time. Thanks.